into something pretty mind-bending. A concept that even stumped Einstein a bit, he called it. Famously, smoky action at a distance.
That's right. We're talking about quantum entanglement.
Exactly. This idea where particles, they stay connected, profoundly linked, really, no matter how far apart they get.
It's like having two coins, maybe. And whenever you toss them, wherever they are, they always land the same. Heads and heads or tails and tails.
But the weird part is, neither coin had a side, like heads or tails, until it actually landed. That's the kind of connected strangeness we're diving into today.
And our mission really is to unpack this powerful idea that this spooky link isn't just some random cosmic weirdness.
Right, not just a glitch.
No, it's actually a direct result, a fundamental consequence of angular momentum. We'll explore how these laws don't just sort of allow entanglement to happen, but they actually design it. They dictate its specific features.
They quantum weirdness, but also the elegance of these fundamental symmetries.
And how these abstract ideas are actually building the future. Quantum computers, unhackable communication. It all connects back.
Let's jump right in. Okay, so keeping those weird coins in mind, what is quantum entanglement really? How do we even start thinking about it?
Well, at its heart, physicists think of entanglement as a kind of physical resource, like energy is a resource classically.
A resource.
Yeah, something you can use for quantum communication, for quantum computing. Formally, it means you've got a system, maybe two or more particles together.
A composite system.
Right. And the state of that whole system just can't be broken down. You can't describe particle A separately from particle B. They're an inseparable whole.
Inseparable, so they lose their individual identities.
In a sense, yes. And this leads to something, well, quite intriguing. If you know everything possible about the total system, say its overall spin, that doesn't mean you know everything about the individual parts. Maximal knowledge of the whole doesn't give you maximal knowledge of the components. They only exist in relation to each other within that shared state.
That really is hard to wrap your head around. So these particles, they're in some kind of limbo state, indefinite, before you measure them.
Exactly. Before measurement, they're in what we call a superposition. All possibilities at once, like that coin spinning in the air, heads and tails simultaneously.
Until it lands.
Until it lands, or until you measure one of the entangled particles. Say you measure an electron spin and you find it's up. That act of measurement, it instantaneously collapses its possibilities into that definite state, up. But it also instantly affects its distant partner.
Instantly, no matter how far.
Instantly. The partner immediately snaps into a perfectly correlated state, maybe down in this case. Across the room or across the galaxy. That's the spooky action part.
And that instantaneous connection, it's non-locality, right?
Yeah.
It just feels like it breaks all the rules. Things influencing each other without touching, faster than light.
It certainly seems to break the rules we're used to. Our intuition screams that influence needs time to travel.
Yeah. So does this mean we can send messages faster than light using this? Because that would be huge and, well, reality breaking.
That's a really crucial point. And the answer, maybe surprisingly, is no. You cannot use this for faster than light communication.
Okay, why not? The influence is instant.
The correlation is instant. But the outcome of any single measurement you make on your particle, it's fundamentally random. You can't force your particle to be up just because you want to send a 1.
Ah, I see. So I measure mine, it's random. The person far away measures theirs, it's random too.
Exactly. You only need the perfect correlation after you get together, maybe phone each other classically, and compare your lists of random results. Then you see the pattern. Up matches down matches up, perfectly. But you needed that slower than light communication to discover the correlation.
Got it. So correlation, yes. Communication, no. Still spooky, though.
Definitely still spooky.
So to really get why this quantum stuff is so different, let's talk about that classical analogy. Bertelsmann's socks. John Bell used this one, right?
Yes, Dr. Bertelsmann and his mismatched socks. A great illustration.
So the idea is Dr. Bertelsmann always wore one pink sock and one, say, green sock. If you see the pink one on his left foot.
You instantly know the right one isn't pink. It must be green. Perfect anti-correlation.
But that's not spooky at all, because the sock colors were fixed from the moment he put them on. They were definite properties all along. You just revealed the pre-existing information.
Exactly. That's classical correlation. It's based on hidden information. Properties that were definite even before you looked.
Okay, that makes perfect sense classically. But you're saying entangled particles aren't like that. Their properties, like spin, aren't predetermined.
That's the absolute core of the quantum difference. Entangled properties are not predetermined. Before you measure that electron spin, it genuinely doesn't have a definite spin. It's in that superposition.
So the correlation isn't revealing hidden information.
No. It emerges from the measurement itself, from that shared, holistic quantum state collapsing. And here's where it gets even stranger. The correlations you get from entanglement are actually stronger than anything you could possibly explain classically.
Stronger. How can they be stronger than perfect correlation?
They violate statistical limits, limits that must hold if the properties were predetermined, like the socks. Quantum mechanics predicts correlations that classical physics just can't reproduce.
And that brings us to John Bell again, doesn't it? In 1964, he found a way to test this.
Precisely. Bell's theorem. It was brilliant. He basically set up a mathematical framework to test this fundamental conflict.
Between quantum mechanics and, what was the alternatives called? Local realism.
Local realism, exactly. The worldview that assumes two things. Realism objects have definite properties, even if unknown, like the socks. And locality, no influence travels faster than light. Common sense, really.
Seems reasonable.
It does. But Bell proved mathematically that local realism puts a strict upper limit on how strong correlations can be. He derived an inequality, often called a Bell inequality, like the CH-SH inequality.
A mathematical boundary for classical correlation.
Yes. And quantum mechanics for entangled particles predicts results that violate this inequality. They go beyond the classical limit.
And the experiments, what did they show?
Overwhelmingly, the experiments confirm quantum mechanics. They show violations of Bell's inequality again and again, which means that local realism, that common sense picture, just doesn't describe our universe at the quantum level. Entanglement is non-classical and non-local.
Okay, let's try to nail down this difference then. Classical correlation, like gloves and boxes, one left, one right, decided from the start, obeys Bell's inequality.
Right, predetermined properties, hidden variables.
But quantum entanglement, it's a single shared state. You can't factor it. The properties are genuinely fuzzy, indefinite until measured. Knowing the whole doesn't mean you know the parts.
And crucially,
It violates Bell's inequality, proving it's fundamentally different.
you've got it. That's the essence of it.
Okay, so we've established it's properly weird, non-classical, non-local. But the big question is how? How does nature pull this off? How does it enforce these correlations that seem stronger than possible? What's the mechanism?
That's the perfect question. And the answer lies in something incredibly fundamental, the conservation laws.
Back to energy momentum.
Exactly. These aren't just, helpful rules we observe. They're bedrock principles.
Yeah.
And they come from something even deeper.
Symmetry.
Symmetry. How does symmetry lead to conservation? Through a beautiful insight by Emmy Noether. Her theorem states that for every continuous symmetry in a physical system, there's a corresponding quantity that must be conserved.
Okay, give me an example.
Sure. The laws of physics don't change over time, right? They're the same today as yesterday. That's time translation symmetry. Noether's theorem tells us this requires energy to be conserved.
Wow. Okay.
Similarly, the laws are the same everywhere in space. Move your lab a meter over, physics still works the same. That's spatial translation symmetry. And it corresponds to the conservation of linear momentum.
And angular momentum.
Comes from rotational symmetry. Physics doesn't care how your lab is oriented. Turn it around, the laws stay the same. So angular momentum must be conserved. There are others too, like electric charge.
So these conservation laws are deeply tied to the fundamental symmetries of the universe. But how do they work in the quantum world, especially with measurements?
Well, the principles carry over, but things get a bit subtle. In quantum mechanics, for an isolated system, it's often the average value, the expectation value, of a conserved quantity that's strictly conserved over time.
The average value. Okay.
But then there's the measurement problem we talked about. You measure a particle in superposition, it suddenly jumps to a definite state. Say its spin changes from maybe up, maybe down to definitely up. That looks like the spin, a form of angular momentum, just changed for that particle.
Yeah, it seems like it just violated conservation of angular momentum right there.
It does seem that way, doesn't it? It feels like the particle just broke the rules.
So how do we resolve that? Where did the momentum or energy go or come from?
The resolution is key, and it brings us right back to entanglement. You have to stop thinking about just the particle. The measurement isn't just something happening to the particle in isolation.
It's an interaction.
It's an interaction. The particle becomes entangled with the measuring device itself. Think bigger. Consider the particle plus the measuring apparatus as one combined, larger quantum system.
Okay, the whole shebang.
The whole shebang. Now, within that larger entangled system, the total conserved quantity, like total angular momentum or total energy, is conserved. It might be redistributed, transferred between the particle and the apparatus, but the total amount remains constant.
Ah, So the conservation law applies to the combined system, the entangled whole. Energy isn't lost, it just moves around within that bigger system during the measurement.
Precisely. That's the crucial aha moment. To see how conservation laws hold up during quantum measurements, you have to include entanglement. The law applies to the inseparable whole. It forces us into this holistic view.
That makes sense. The rules apply just on a grander entangled scale.
Exactly. Okay, so now we see how conservation laws operate in the quantum realm, even with measurements. Let's look at some specific examples where these laws don't just permit entanglement, but actively create it, shape it.
Sounds good. Where do we start?
Let's start something natural. Particle decay. Happens all the time. An unstable particle falls apart into lighter ones. And this process is absolutely governed by conservation laws, which means, as we'll see, the resulting particles have to be entangled.
Have to be. Okay, show me.
Let's take a classic example. The decay of a neutral pion. It's a subatomic particle. Importantly, it has zero total spin. Spin is a type of angular momentum.
Zero spin initially. And it decays into...
two high-energy photons. Gamma rays, essentially. Packets of light.
Okay. Zero spin pion becomes 2 photons. How does conservation shape this?
Angular momentum must be conserved. The pion started with 0, so the total angular momentum of the 2 photons after the decay must also add up to 0.
Makes sense.
Now, photons have spin related to their polarization. Let's say one photon comes out right-hand circular polarized, RHC, which corresponds to a spin projection along its path. For the total to be 0, the other photon, flying in the opposite direction, must also be RHC polarized when viewed along its own path. The same logic applies if the first photon is left-hand circular, LHC.
So either both RHC or both LHC relative to their directions to keep the total spin 0.
Exactly. But quantum mechanics says the final state isn't one or the other. It's a superposition of both possibilities, both RHC plus both LHC.
So neither photon has a definite polarization until you measure it.
Correct. But the instant you measure one and find it's RHC, you know the other must also be RHC. They are perfectly correlated.
And that perfect correlation is required by the conservation of angular momentum.
Mandated. It's the only way for the decay to happen without violating the conservation law. Entanglement is baked in by the symmetry requirement.
That's really clear. And are other laws involved too?
Oh, yes. Momentum conservation plays a huge role. If the pion was at rest before decaying, it had 0 linear momentum.
Right.
So the 2 photons must fly off in exactly opposite directions with equal momentum magnitudes. Their vector momenta have to sum to 0. Measure one going left, the other must be going right. Another perfect correlation.
And energy.
Energy conservation, too. The pion's rest mass energy is completely converted into the energy of the 2 photons. So the sum of the photon energies is fixed, determined by the pion's mass. They share the energy budget, creating a correlation in their frequencies.
So all these laws, angular momentum, linear momentum, energy, they all have to be satisfied simultaneously.
Yes, they're interlocking constraints. And the only way nature can satisfy all of them at once in this decay is by producing the photons in this specific, highly correlated, entangled state. The decay literally must produce entanglement to be physically possible.
Wow. Nature uses entanglement to balance its books. Okay, that's a natural source.
Uh-huh.
What about how we make entanglement in the lab? You mentioned that earlier.
Right. The workhorse technique there is called spontaneous parametric down conversion. SPDC for short.
SPDC, what happens there?
You start with a laser, producing high-energy pump photons. You shine this laser beam through a special kind of crystal, like BBO, barium borate.
Okay, laser through crystal.
And inside that crystal, a small fraction of those pump photons will spontaneously split into 2 new photons, which are lower in energy. We call them the signal and idler photons.
1 photon becomes 2. And they come out entangled.
Yes, often highly entangled. And again, it's the conservation laws doing the work. The whole process hinges on something called the phase matching condition.
Phase matching. Sounds technical.
It sounds technical, but it's really just the explicit statement that energy and momentum must be conserved simultaneously during that splitting process inside the crystal.
Okay, so it's conservation laws again, just maybe phrased differently for light in a crystal.
Exactly. Energy conservation means the energy of the incoming pump photon must exactly equal the sum of the energies of the outgoing signal and idler photons. E-pump is signal plus idler.
Which means their frequencies, their colors, must be perfectly correlated.
Perfectly correlated. If you know the pump frequency and measure the signal frequency, you instantly know the idler frequency.
And momentum.
Momentum conservation also applies. The momentum vector of the pump photon must equal the vector sum of the signal and idler momenta. P pump equals signal plus Pidler.
What does that lead to?
This creates really strong spatial correlations. The signal and idler photons don't just fly off anywhere. They emerge at specific angles relative to the pump beam, often in cones. Their directions are linked.
So correlations in energy, frequency, and momentum direction.
Yeah.
What about angular momentum, like spin or polarization?
Absolutely. That can be conserved too. If the pump photon carries spin angular momentum polarization or even orbital angular momentum related to the shape of its wavefront, the signal and idler photons must share that initial angular momentum. Their individual states might be indefinite, but their sum must match the pumps, entangling them in polarization or OAM.
And the cool thing about SPDC is that scientists can control this, right? They can engineer different types of entanglement.
That's the power of it. By choosing this specific crystal, its orientation, the pump laser properties, you can fine-tune which conservation rules are most prominent and engineer different kinds of entangled states on demand. Polarization entanglement, energy-time entanglement, momentum entanglement, OAM entanglement.
So the conservation laws are like gatekeepers.
That's a great way to put it. They're active and unforgiving gatekeepers. Only those potential photon-splitting events where the daughter photons perfectly conserve the pump's energy momentum and angular momentum are allowed to actually happen, to become real.
The photons are essentially born entangled because their very existence depends on fulfilling these conservation requirements together.
Precisely. The laws dictate the entanglement from the very start.
Okay, so we've seen the theory. Conservation laws seem to force entanglement into existence both naturally and in the lab. But could there still be a loophole? Could these correlations, even though strong, somehow still be classical underneath, like super sophisticated Bertelsmann socks?
That's exactly the question John Bell tackled. How do we know for sure these correlations are truly quantum and non-local, and not just some very clever classical imitation?
His theorem was the key.
His theorem provided the theoretical test, yes. Remember, he showed that any local hidden variable theory, any theory based on pre-existing properties and no faster-than-light influence, has that mathematical limit, the Bell inequality.
The classical ceiling on correlations.
Right. Quantum mechanics predicts violations of that ceiling. So the crucial step was to do the experiment. Can we actually measure correlations strong enough to break through that classical ceiling?
And that brings us to Alain Aspect and his team in the early 80s. What did they do?
They performed one of the first really convincing Bell tests. They used pairs of photons entangled in polarization generated from calcium atoms decaying.
Okay.
They sent these photons in opposite directions to polarizers about 12 meters apart, and here's the crucial part. They changed the orientation settings of these polarizers very rapidly.
While the photons were already flying.
Yes. While the photons were in flight, they used a pseudo-random switching mechanism. This was vital to rule out the possibility that the polarizers could somehow communicate classically, slower than light, to coordinate their settings and fake the correlation.
Closing the locality loophole, essentially, or trying to.
Exactly. Right. Trying to ensure the settings were chosen independently and too fast for any hidden classical signal to travel between them.
And the results? Did they break the Bell limit?
They did. Clearly and significantly. They measured a correlation value, specifically the S's value in the CHSH inequality, of about 2.7. The classical limit is 2.
Wow. So significantly above the classical ceiling.
Yes. It was 2.697 plus or minus 0.015, if I recall correctly, in excellent agreement with the quantum mechanical prediction and way beyond the classical limit of 2.
A landmark result. It showed the spooky correlations weren't just theory. They were real, measurable, and demonstrably non-classical.
It was powerful confirmation that the non-local correlations required by conservation laws are indeed the ones nature uses. Nature's way of upholding symmetry is fundamentally non-local.
Now, I remember reading that even Aspect's experiments had some potential criticisms or loopholes initially.
Yes, that's true. No experiment is perfect, especially early ones. Critics pointed out a couple of things. One was the locality loophole. Maybe the settings weren't truly random or independent. The other was the detection loophole.
Detection loophole.
Yeah, the photon detectors back then weren't very efficient. They missed a lot of photons. So the worry was maybe the detectors were only clicking for a biased subset of pairs that did obey the inequality, and we just weren't seeing the full picture. Maybe if we detected all pairs, the correlation would fall back below the classical limit.
Okay. Valid concerns. Have those been addressed since then?
Oh, absolutely. There's been a huge amount of experimental work over the last few decades. Especially around 2015, several groups performed what are called loophole-free Bell tests.
Loophole-free, meaning they close both loopholes at the same time.
Yes, simultaneously. Using different systems like entangled electrons and diamond defects separated by over a kilometer, combined with very high-efficiency detectors. These experiments decisively closed both the locality and detection loopholes in one go.
So making the case even stronger.
Much stronger. And people even got creative addressing residual concerns, like the freedom of choice loophole. Could the choice of measurement settings somehow be predetermined by some common cause way back in the past?
That sounds pretty philosophical.
It does. But experimenters tackled it. Some teams used light signals from incredibly distant quasars, billions of light years away, arriving from opposite sides of the sky, to randomly determine their measurement settings.
Using cosmic randomness.
Yeah.
The idea being that it's cosmologically implausible for some hidden variable on Earth to have influenced both those quasars billions of years ago and the particle source.
Precisely, making any classical coordination mechanism incredibly far-fetched.
And the results of these loophole-free and cosmic Bell tests.
Still the same. Clear, unambiguous violation of Bell's inequalities, matching quantum predictions perfectly.
So the bottom line is?
The bottom line is that the violation of Bell's inequalities is now one of the most solidly established empirical facts in physics. The chain of logic holds. Conservation laws mandate these strong, non-local correlations. Bell proved these correlations are beyond classical explanation, and experiments have proven Bell right. Nature is non-local in this way.
Nature's method for upholding symmetry is fundamentally quantum and spooky. There's really no escaping it.
That seems to be the reality we live in. Okay, let's pull this all together. We looked at particle decay, a natural process. We looked at SPDC, engineered in the lab. What's the common thread?
In both cases, when a system changes, like a pion decaying or a pump photon splitting, the outcome isn't arbitrary. It's tightly controlled.
By what?
By the conservation laws.
Yeah.
Energy, momentum, angular momentum. They act like a strict blueprint.
Exactly. A blueprint that dictates the precise mathematical form of the entanglement between the resulting particles.
So for the pion decay, energy conservation fixes the total energy of the photons. Momentum conservation makes them fly back to back. Angular momentum conservation correlates their polarizations, both RHC or both LHC.
Right. And for SPDC, energy conservation links their frequencies. Momentum conservation links their directions through phase matching. Angular momentum conservation can link their polarizations or OAM states.
So entanglement isn't just consistent with conservation laws. It seems to be the very language quantum mechanics uses to ensure those laws are always obeyed, even across vast distances, for these inseparable systems.
That's a beautiful way to put it. It's the framework for maintaining global symmetries non-locally.
And this isn't just, fascinating physics philosophy. You said earlier it's a resource. How is this conservation-mandated entanglement actually being used?
It's absolutely fundamental to the whole field of quantum information science. Take quantum computing.
The big one.
Right. The potential power of quantum computers comes from harnessing superposition and, crucially, entanglement. Qubits, the basic units, can be linked together in these complex entangled states.
Allowing for things like quantum parallelism.
Yes. Algorithms like Shor's algorithm, famous for potentially breaking current encryption by factoring large numbers super fast.
It relies on entanglement.
Heavily. It needs to create and manipulate these large-scale, multi-particle entangled states. The fact that these correlations are reliable, that they're guaranteed by fundamental conservation laws, is what makes such algorithms even conceivable. The stability of the entanglement matters.
Okay, so quantum computing depends on it. What about quantum cryptography? Unhackable communication.
That's another direct application and maybe even clearer link to Bell's theorem and conservation. There are protocols, like one called Eckert 91, that use entanglement directly for security.
How does that work?
Basically, two parties, let's call them Alice and Bob, share pairs of entangled particles. They can then perform measurements on their particles, choosing settings randomly, just like in a Bell test.
Okay, they do a Bell test on their communication channel.
Essentially, yes. They communicate classically afterwards to compare a subset of their results and check if they violate a Bell inequality.
And if they do violate it?
If they see the strong quantum correlations that violate the classical limit, it does two things. First, it confirms they actually share a genuine quantum entangled resource mandated by those conservation laws. Second, and this is the security part, it proves that no eavesdropper, say Eve, could have intercepted and measured the particles without disturbing them.
Why not? How does eavesdropping break the correlation?
Because any attempt by Eve to measure the particle en route would inevitably collapse the delicate quantum state. It would break that perfect, conservation-mandated correlation between Alice's and Bob's particles. When Alice and Bob do their Bell test, they wouldn't see a violation anymore. The correlation would look classical or just noisy.
So the Bell violation acts as a tamper evidence seal. If it's violated, the line is secure. If not, someone's been listening.
Exactly. It's incredibly elegant. You're using the fundamental laws of physics, conservation, as your guarantee of the entangled pair's properties, and Bell's theorem as your test for the channel's integrity.
It's like conservation laws are the factory spec sheet for the entangled particles, and the Bell test is the quality control check on arrival.
That's a perfect analogy.
It really shows how these deep, almost philosophical principles about symmetry and conservation are becoming tangible tools for technology. Incredible.
It really is, from abstract concepts to practical devices. So, just to recap where we've landed, we started with this idea. Maybe entanglement is just a consequence of conservation laws. But I think our dive showed something deeper.
Yeah, it seems like entanglement is more than just a consequence. It feels like it's the way nature makes sure all the conservation laws, energy, momentum, angular momentum, hold true for systems that are fundamentally connected but physically separated.
It's the essential quantum framework for upholding those global symmetries non-locally. That spookiness we talked about, it's not a bug, it's a feature. It's precisely what's needed to maintain the universe's fundamental rules in a quantum world.
And thinking about it that way, it really forces a shift in perspective, doesn't it? Away from just looking at individual parts towards this holistic view.
Profoundly holistic and non-separable. The properties of the entangled system truly belong to the whole system. Conservation applies to the whole.
It flips Einstein's spooky action on its head. It's not some weird anomaly. It's an elegant, necessary consequence of the universe's symmetries. It's how nature keeps its books balanced across space and time.
Beautifully put. It transforms the paradox into a principle. And the implications go beyond just physics. Philosophically, it really challenges our everyday classical ideas about reality, about what it means for things to be separate, about cause and effect across distances. It points towards a universe that's much more interconnected than we usually assume.
And practically, as we discussed, this deep understanding isn't just academic anymore. Being able to reliably create and verify these conservation-mandated, entangled states, that's what's driving this second quantum revolution.
Quantum computers, quantum cryptography, ultra-sensitive quantum sensors, they all stem from harnessing these fundamental non-local connections.
It's amazing. We've gone from a concept that deeply troubled the founders of quantum theory, something that seemed like a flaw or a paradox,
To it becoming a key resource for building the technologies that will likely shape the 21st century and beyond.
It really shows that the universe isn't just stranger than we imagine, it might be stranger than we can imagine.
Indeed. And here's a final thought to leave you with. If entanglement is so deeply tied to fundamental symmetries and conservation laws, and we know space-time geometry itself is linked to energy and momentum via Einstein's theories, could entanglement and these symmetries be clues about the very fabric of space-time at the quantum level?
You mean in a future theory of quantum gravity? Could entanglement somehow be the connection, the threads weaving space-time together?
It's a very speculative idea, of course, way beyond what we know for sure, but it shows just how deep these connections might run. Thinking about how fundamental symmetries manifest through entanglement might be a path towards understanding reality at its deepest level, something to ponder.